Hello students, welcome to GCE Connect series of lectures. In today's lecture we are going to discuss about Bernoulli's equation. So we have already derived Bernoulli's equation by using Euler's equation of fluid motion, but actually how the Bernoulli's equation can be obtained, so we'll see in this today's session. So Daniel Bernoulli, a scientist, so he is a Daniel Bernoulli. So he was in the year 1700 to 1782. So his name is Daniel Bernoulli, a Swiss physicist and a mathematician, made important discoveries in fluid dynamics and born into a family of mathematicians. He was the only member of the family to make a mark in physics. Bernoulli's most famous work, Hydrodynamica, was published in 1738. So it is both theoretical and practical study of equilibrium, pressure and speed in fluids. And he also showed that as the speed of the fluid increases, its pressure decreases. As the speed of fluid increases, its pressure decreases. And in Hydrodynamica, Bernoulli also attempted the first explanation of the behavior of gases with changing pressure and temperature. This was the beginning of kinetic theory of gases. So the Bernoulli's equation in this dynamics of fluid flow we are going to use is very useful for analyzing fluid motion. So let us look at this example here. So here when you press your thumb over the end of garden hose pipe, see, look here, this person is pressing the thumb at the end of the garden hose pipe. So what will happen here? The opening becomes a very narrow, or you can call it as a very small slit. Then the water comes out at a high speed. Look here, at this point here, a person is pressing a garden hose pipe, and the liquid or the water which is coming out of this end, it is coming like a jet. Okay, so here what happens? You are reducing the area of passing of fluid. So what will happen? The opening becomes a very small slit. The water comes out with a very high speed, and so here, is the water under a greater pressure when it is inside the hose, or when it is out in the air? You can answer this question by noting how hard you have to push your thumb greater against the water inside the end of the hose. So the pressure inside the hose is definitely greater. Here the pressure inside the hose is definitely greater than the atmospheric pressure, whatever the pressure is outside. So compared to the atmospheric pressure, the pressure inside the hose pipe definitely will be greater. And at this point where you are pressing the pipe, there the area will be reduced, so the velocity of fluid increases. So that's why you are getting the liquid as a jet of water. Okay, so then there is a relation between a velocity and a pressure. So the relationship between the fluid speed, the pressure and elevation was first derived by Daniel Bernoulli in the year 38. So he has given the relation between velocity and pressure and elevation. He has given the relation between velocity, pressure and elevation. velocity, pressure and elevation, there is a relation between these. So that is what we call as a Bernoulli's equation of fluid motion. So next, as I said, there is a relation between fluid speed, pressure and elevation was first derived in 1738 by the Swiss physicist Daniel Bernoulli. So consider the flow of an ideal fluid. So as you all know what you mean by ideal fluid, the fluid which doesn't have any viscosity, or it is called as a non-viscous fluid, what we call as the ideal fluid. And for the derivation purpose, for the analysis purpose, the ideal fluid will possess certain characteristics and also certain assumptions to be made for deriving the Bernoulli equation. So consider the flow of fluid, that is ideal fluid, through a non-uniform pipe in a time t as illustrated in the following figure. Let's look at this picture here. This is a non-uniform pipe. Okay, so let us take, this is the section 1 and this is the section 2 here. This is the section 2 and this is the section 1. So here let us call the lower shaded part, that is this one, the lower shaded part section 1, and the upper shaded section as shaded part as a section 2. Then the force exerted by the fluid in section 1 has a magnitude. Here the force exerted by the fluid in section 1, here the fluid in section 1, that is pressure into area. As you know, pressure equal to what? Force by area. As you know, pressure equal to force by area. Then the force equal to what? Pressure into area. Force equal to what? Pressure into area. So since the pressure force we are taking at section 1, so it is written as P1 into A1. That is, the force exerted by the fluid in section 1 has a magnitude P1 A1. Then the work done by this force. So if you want to lift a water from lower elevation to higher elevation, this is the lower elevation. So or from the lower position to higher position, if you want to lift water here, so if you need to apply a certain sort of force to lift the water from this position to this position, then we call, when the water is the liquid is being lifting from this position to this position, we call it as a work is being done. Then the work done by this force in a time t is, it is the work done by this force, this whatever the force you are applying here, that is P1 A1, the work done by this force in time t is given as W1 as F1 into delta x1, F1 into delta x1. Here the force acting is F1. Because of the F1 is nothing but P1 into A1. Because of F1 there is a work done, that is F1 multiplied by delta x1. So delta x1, but delta x1 but F1 is what? P1 into A1 into delta x1. Then area multiplied by length or the distance, what we call as a volume. So P1 into V. See here, you are applying a force, then the liquid is moving in this direction and it has covered a certain distance, it is delta x1. So force multiplied by distance is work done, that is force into displacement is the work done. Then again we can write force as P1 into A1, A1 into delta x1 is what? Volume, okay, where V is the volume of section 1. Similarly, the work done by the fluid in section 2 in the same time t is given as, similarly here at this position, the work done by the fluid in section 2 in the same time t is given as W2 equal to minus P2 A2 into delta X2 is equal to minus P2 into V, again where V is the volume of the section. Now the volume that passes through section 1, that is the volume that passes through the section 1 in a time t equals the volume that passes through the section 2 in the same time. So here the volume, whatever the volume of liquid passing through this section 1 in time t will be same the volume of water passing through the section 2 here. Then next, this work is negative. Here I have taken this work is negative because the fluid force opposes the displacement. At this position the fluid force opposes the displacement here. Okay, opposes the displacement. Thus the net work done by these forces in the time t is given as, so here also the force and here also the force. Here we are applying a force in this direction, and opposite to that again one more force is acting. Then the net force acting on this is given as so W equal to this one, P1 minus P2 into V. So this is the net force acting, or the net work done by these forces in the time t is W, that is P1 V minus P2 V. Hope you understood this one. So the net force will be, that is W is equal to P1 A1 again minus P2 A2. So already the negative sign is being considered here. Okay. This is the net work done here. Then part of this work goes into changing the kinetic energy. Yes. The kinetic energy keep on changing here. The part of this work goes into changing the kinetic energy of the fluid, and part goes into changing the gravitational potential energy. Okay. If m is the mass that enters one end and leaves the other end in a time t, then change in kinetic energy of this mass is delta k is half mv square. Means you can take the kinetic energy here and here, the change in kinetic energy we get. As with this statement, that as the kinetic energy changes, the potential energy also changes. At this position, if you take the kinetic energy here and also the kinetic energy here, so here the kinetic energy will be less, the potential energy will be more. Here the kinetic energy is more, the potential energy is less. Means the part of this work goes into changing. Means here you are applying a force, here the fluid is having a very high velocity, so the kinetic energy is more here compared to the potential energy, and this part of the kinetic energy goes on changing the gravitational potential energy. Here the potential energy will be increasing, kinetic energy get decreases. So if m is the mass that enters one end and leaves the other end in a time t, then the change in kinetic energy of this mass is delta k. The change in kinetic energy will be half mv square. Means this here, this part, this end kinetic energy, that is half mv2 square minus half mv1 square. The change in gravitational potential energy, what we get as delta u. Delta u is a change in potential energy. So here mgy2, so the potential energy we can write mgy2, here mgy1. The change is what? This minus this one, mgy2 minus mgy1. So we can apply the equation, that is work energy principle, that is work done is equal to kinetic energy plus change in potential energy, total work done. So with this equation, if you substitute above equations here, we get the finally this one. We simplify this one. Okay, if we divide each term by V, that is volume, and recall that density equal to mass by volume. You all know the density equal to mass by volume. This expression reduces to, so if you divide the entire equation by V, it is volume P1 minus P2 is equal to this half rho V2 square minus half rho V1 square, then plus rho G Y2 minus rho G Y1 we get, and rearranging the terms, then we get this equation. So we get this equation, and this is what we call as a Bernoulli's equation as applied to an ideal fluid, and it is expressed as P plus half rho V square plus rho into G into Y is equal to constant. Okay, is equal to constant. Then this expression specifies that in a laminar flow, the sum of pressure, kinetic, energy per unit volume and gravitational potential energy per unit volume has the same value at all the points along the streamline. So I'll repeat, the sum of pressure energy, kinetic energy and potential energy per unit volume has the same value at all the points along the streamline. So this is what we call as a Bernoulli's equation. Okay, this is Bernoulli's equation. And when the fluid is at rest, so we can take a V1 equal to V2 equal to 0, then the above equation becomes P1 minus P2, that is rho into G Y2 minus Y1. So we can write it as a hydrostatic law, that is rho into G into H. Okay, so this is fluid at rest. If the fluid is under motion, this is the equation to be used. What it indicates, the pressure is inversely proportional to velocity. As the velocity decreases, the pressure increases. As the velocity increases, the pressure decreases. Okay, so this is what we call as a Bernoulli's principle. If the velocity increases, means the pressure decreases. So if the velocity increases, pressure at that point will be decreasing. If the velocity increases, pressure decreases, and if the velocity decreases, pressure increases. Okay, this is Bernoulli's equation. So just practice this equation and try to understand each and every term here. Okay, so we'll continue in the next session. Thank you.